Physics Critical Thinking Assignment 1, Electrostatic Charges. And here's the homework that is due Tuesday night. I'm calling it E136, Electrostatics 136. You have a charge on a string, and it's making an angle theta. You'll need to rank these by the size of this angle here. There's an electric field depicted by these arrows to the right, and it's saying it's a positive charge. Well, it's listed as positive charges unless it says negative. They're positive. And it tells you the mass of the charge. All right, there's also some good review in here on vectors and free body diagrams, which is where you want to start this problem. So here are some hints. If I scroll down, okay. So here's the free body diagram on the left here. That says T there. That's cut off a little bit. That's a T. So we have tension in that string at that theta angle. That's the same angle as the angle in a diagram if you follow the rules of alternate interior angles from geometry. There's an electrical force to the right, which is trying to make the particle go to the right. And then there's a force of gravity straight down. So there's three forces acting on that charged particle. The particle at an angle you have to break up into its components, or the force at an angle, the tension, T. You could call it F sub T if you want. But once again, following our basic rules for components, cosine of that angle is T sub y over T. So if you solve that for T sub y, you get T sub y equals T cosine theta. And likewise, using sine of theta, you get T sub x equals T sine theta. The blue diagram is probably the more important one as far as kind of getting an idea of how to balance this out. We have static equilibrium. So I got rid of T, so I'm replacing the T force with its two components, which are equivalent to the tension force. This is in static equilibrium, therefore the up force, T sub y, equals the down force, force of gravity. So I put that in blue right here. And then left and right, same thing, T sub x equals the force, electric force, to the right. And this is from, I think, unit 18. E equals F over Q, electric force. And if you solve that for F, F equals EQ. So what I'm doing here, I'm doing a lot of preliminary work here that is a good way to approach this problem. But if we have T sub x, which I get from way over here on the left, T sub x is T sine theta. I plug that in for T sub x, bring it over here. And then I plug in for F sub E, which is EQ. So I'm plugging in this into here. So I get that red equation right there. Going back to the blue equation. Up and down, we have T sub y equals F sub g. Plugging in for T sub y is T cosine theta. Force of gravity is mg, mass times gravity. So I plugged in for both of those. And then I did a little tricky thing here. Tricky. I'm taking this red equation and basically dividing it by the blue equation. All right, it's something we typically probably wouldn't think to do. But you'll see it helps us solve this problem greatly. So that ends up with T sine theta equals EQ divided by T cosine theta times mg. The t's cancel out. All right. Then something you may or may not remember from trig. Sine over cosine is tangent of an angle, if it's the same angle, which it is in both cases here. So we have tangent of theta of that angle that's of interest equals the ratio EQ over mg, where E is was the electric field strength, Q is the charge on the particle, m and g. Now, the bigger this ratio is, then the bigger the tangent of theta is, because that's equal to tangent theta. And the bigger the tangent theta is, the greater the theta, because for theta between 0 and 90, as the tangent of theta goes up, so does the angle. Or conversely, as the angle gets bigger, the tangent gets bigger, if you look at the tangent function. That's as far as I'm going to go with this. Now you have to finish it off. It's due on Tuesday night at midnight. But things to keep in mind here for this last equation, which is central to look at. E is the same for all 6 particles. And G is 9.8 for all 6 particles. The only thing that's different for all 6 particles is Q and M. So think about that as you finish off the ranking there. So that's the ranking problem that is due. It's number 136. Okay, other ones that we have. Let's go here. Okay, let me see if I can make this bigger. There we go. Oops, a little too big maybe. Okay. You have 3 collinear charges. I've done a lot of preliminary work here. And I'm not doing all cases. And once again, I could have some kind of variation on this kind of problem on a test. But you have 3 charges here, A, B, and C, collinear, and we have like 7 or 8 scenarios. The main equation for the force between any 2 particles is over here, Coulomb's law, F equals KQQ over R squared. We did some problems like this in the notes. But looking at the first case here, you can only calculate the force for any 2 particles at a time. So if you just look at particle A and B, they're both positive. So I've depicted that with red arrows, that they're repelling each other. And the 1 here is just, I could have left the 1 off. I'm just showing that those match up. And I did red. I'm showing that with red. So those are the 2 matching arrows. They're the same 2 matching forces, the same size force, according to Newton's third law, and the equation anyway is Coulomb's law. They repel each other with an equal and opposite force. So I'm depicting that in red and then calling it step 1. The 1 is not the size of the charge. In fact, the next step, well, the blue ones, number 2, I've drawn those as shorter arrows, but they might not be weaker forces. They might be bigger forces because it doesn't tell you the size of these charges. If I adjusted this problem and said, oh, if all the charges all had the same size charge, they're all 1 Coulomb or whatever, then the blue force between B and C, repelling because they're like charges, would be weaker because that distance, it tells you that the distance from B to C is twice the distance from A to B. It does tell you that in the problem, I believe. Yeah, twice the distance. So actually those blue arrows would be 1/4, because if you double the distance, if you go back to the equation over here, if you double the distance, you'll have 1/4 the force if you have the same size charges. So if the red forces were 4 newtons, then the blue ones would be 1 newton. They'd be 1/4 of that if they were all the same charge. Well, we don't know that they're the same size charge. Charge C could be a really, really large charge. It could be 4 times the amount of charge as A, in which case the blue forces would equal the red forces. Because it gives us that in the problem. We don't know what size these charges are. So we don't technically know how big these forces are. Just the main thing here right now is what direction they're going. That's the main thing for the analysis of the solution. In part, well, the next thing is matching up A and C. They're both positive charges, so they repel as well. So I've labeled that with the 3, these little black arrows here showing the repelling. And that's the directional thing. Once again, we don't know how big they are. They could be bigger than the red arrows. They could be bigger than the blue arrows, the blue forces, depending on the size of each of these charges. Now, let's answer the question for this one going along. It says the sum of the charges on sum of the forces on charge A. In other words, the net force on charge A. Well, something's wrong here. That shouldn't say. Well, that says possibly 0. On A, it must be non-zero. Charge A must have a non-zero, because it has 2 forces to the left. There's no way that it could add up. It can't add up to 0. It's going to have a force to the left. So this is the wrong X here. On B, it's possibly 0. The force on B is possibly 0 because the red number 1 and the blue number 2 could be the same size. They're opposites. So what you're going to see here is if the 2 arrows are opposed to each other, they could add up to be 0, possibly 0, not necessarily 0. And if all these charges were the same size, like I mentioned before, it would not be 0 because the red force would be bigger than the blue force. And then the charge on C, the net force on C must be non-zero. It's got to be to the right because the 2 forces are both to the right. Let's skip one and go to let's go to the one down here lower. Let's go to this line here, the 3rd line. Once again, it's all a directional thing. So I'm just going by directions. I'm going to start with red. So A and B are opposites of positive and minus. I don't know what size charge the forces are, but I know they attract. So that's why I put them towards each other. B and C attract. That's why I show them attracting, because you have a negative and positive. And then A and C repel because they're both positives. So the bottom line here is once you have all the arrows drawn on a diagram, and we don't know how big they are, but we know the directions, all three cases there could be a net force of 0 on any one of these three charges. It's not possible for all three at the same time to be a net 0 because of the difference in the spacings. But it could be each one individually. The net force on A could be 0. The net force on B could be 0. So all possibly 0 in all cases, because the arrows could subtract off to give us 0 depending on the size of the charges. I'll do one or two more here. Let's go down to this one. Like I say, you can see I'm skipping some things here. But in this case right here, the red represents A and B attracting. They're opposites. The blue representing 2 repelling because they're both plus. And then looking at A and C, they attract. The third pair of arrows attracting. And then once again, you can see the pattern. The net force on A and B must be non-zero. And for C, it possibly could be 0. Once again, whenever the two arrows are opposed to each other, you get a possibly 0 answer. And that's how you approach each of these problems. So that's how you find the solutions for each individual part of this. That's number 2, or what I call E31. All right. Next problem. E32. Okay, you're trying to find rank these by the net force on the lower left particle. Given this equilateral triangle configuration, all three charges are the same distance apart. Once again, it's Coulomb's law up here, F equals kqq over r squared. Now if you factor out the k over the r squared, I'm going to simplify the problem. If I say the distance here on each side of this triangle is, say, 1 meter, or whatever it is, it doesn't matter. All of these distances from particle 1, if you call these three particles 1, 2, and 3 particles, they all have the same distance apart. Q1, Q2, Q3, whatever you want to call them. We're going to take them 2 at a time, which is what you have to do when you do Coulomb's law, 2 charges at a time. But bottom line is the k over the r squared doesn't matter. Because in each case, because we're just looking at the magnitude of the overall force, not the actual absolute number. You can put in actual numbers and calculate actual numbers here. That would make the problem go a little bit longer, but it would be a good way to do the problem. But bottom line is the force of attraction or repulsion is going to be proportional to Q1 times Q2. That's all we have to look at to compare, if we're just comparing each of these situations. And we can only do that if it's the same distance in all cases, which it is. The same r in all cases. That's why I can ignore that, because they all have the same r. Or just call it 1 meter. So I draw the diagrams first. All right. So for example, if I'm just looking at the lower left, along the bottom, you have the 2q and a q. They repel each other. I didn't show you the other force on the little q on the right would be a repelling force like I did in the previous problem, because I don't really care about that charge. It says we're only going to look at the net force on its bottom left corner. So they repel each other. And if I just look at the F equals QQ, bottom line, if I take 2Q times Q, or look at the coefficient in front of them, and let my Q be 1 Coulomb. So let the Q equal 1. So let R equal 1, I could even write that down. Let R equal 1 meter. And the units don't matter as long as you're consistent. And let Q equal 1 Coulomb. You don't even need to write that down. If I plug that in and let K, the value for K, be 1 instead of the 9.0 times 10 to the 9th. Bottom line is, it's basically, you look at the coefficient, 2 times 1, 1Q is 2Q. So the force there, compared to the other forces, will be a size or magnitude of 2 newtons. Units don't matter as long as you're using the same units in all of these. And then along the left side here, a 2Q and a 2Q, basically you're multiplying the two charges. 2Q times 2Q is 4Q squared, Q being 1, you get a size of 4. So that vector is twice as long. But they're at a 60-degree angle there. We'll come back to that angle in a little bit. Because these are going to be vectors we have to add up to get the net force. On the next one here, along the bottom, same thing. It's a Q times 2Q gives me a 2, a magnitude of 2. And along the left side, it's 2q times q, magnitude of 2. But I'm also giving you the direction along the line of the connection between those two left-hand side particles. That's how I got the 4 over here as well. It's always lined up with the line joining the two charges. So that's a 2 and a 2. I can already tell you the net force of these two charges is less than the net force of these two charges because they're both at 60-degree orientations, but I have a larger force right there. We'll come back to that. Okay. So this one here. All right. Bottom, q times -1 would be -2, but I don't need to put the negative in there. I've included that with the arrow. This means it's an attractive. They attract each other. Once again, I don't care about the force on the negative q. I could redo this problem and just say, redo the whole problem for the right-hand charge or the top charge. So that would be another good way to tweak this problem for a test. Could do that. That's why I need to have you copy all these and have these ready to go in a test. I'll try to include them if I have a problem like this in a test, but also if your diagrams don't download in a test, these will be available. Make sure you have these copies ready to go when you take the test. A print copy of these. All right. So it's 2q times q is 2. But on the left-hand side, we have a 0 charge up there, so there'll be a 0 force. So the force is just 2. That's the actual magnitude of that force is 2 newtons. So I keep going and doing that. On this one over here, on the bottom, it's 2q times q, 2 to the right because of the negative, they attract. And then along the left-hand side, once again, I get a 2, just like in case B. And then case E is a lot like case A. We got the 4 down and to the left, but then we also have 4 straight to the left. So it's just like case A, except for now we have a 4 and a 4 instead of 2 and a 4. And then case F, along the bottom they attract, 4 and 4. So those are my 6 diagrams. Now, if you put actual real numbers in here and angles and find all the components, this could be not a nightmare, but it'd be a lot of work if you want to do these all by vector addition. But we have to rank these, and we can use some common sense and just rational thinking here to show you that here are the 6 diagrams at the bottom here. In case A, you have a force of 2 to the left and 4 at an angle down. The angle between them is 60 degrees, but I know the result, R is the result of add those two together, is going to be bigger than 4. The result of adding those two vectors is more than 4. All right, but less than 6. Because the only way to get 6 is if the 4 and the 2 are directly adding in the same exact direction. But I know it's more than 4. If the angle is 90, it's still more than 4. Pythagorean theorem would even show that if the angle between them was 90, 2 squared plus 4 squared equals whatever r squared is, would be more than 4 even at 90 degrees. But at 60 degrees, it's even a bigger net force. In case B, the result has to be bigger than 2, but less than 4. Because the only way to get 4 summation of those two vectors is if they were lined up. But I do know it's less than 4, more than 2. If that angle is less than 60, or 60, less than 90, it can't be greater than 4. All right, but it's greater than 2. Somewhere between 2 and 4. And part C, it's 2. Part D, all right, the actual angle resultant is 2, because if you look at the geometry, if you draw this geometry and the way it's set up, this diagonal right here, R, the blue vector, actually splits that parallelogram into 2 equilateral triangles. So you can do the trig there that we have 2 60 60 60 triangles. In other words, if you have an equilateral equal angular triangle, 60 60 60, the sides are all the same. So that result there, you can prove it trigonometrically that that's the same size as the sides, 2. So that's a 2. In E, I have R is much greater than 4. Much, much greater. I'm just trying to make the argument that if I'm comparing E to A, okay, the answer for E is going to be more than the answer to A, because we have the same angles involved, but we have one force that's bigger. The 4 on the top is bigger than the 2, so the net result is this R here has to be bigger than the one in A. That's the important thing there. And F is like D. It's equilateral triangles. If you look at the angles there, that diagonal has a magnitude of 4 units, 4 newtons. So the ranking is going to be E has to be the greatest net force, just based on these diagrams. Then A, which is bigger than 4, okay, but less than the ranking for E. F has to be slightly less than 4, so it has to be the next ranking. And then, well, F, I'm sorry, F was 4. Sorry, F was 4. A was greater than 4. F is 4. B has to be less than 4, but bigger than 2. In this diagram right here. Then finally, C and D are 2. So that's the ranking. All right, number 58, electrostatic fields. Here's an interesting one. We have 3 collinear charges. 3 charges in a line. Now we're asking for the electric field at the location of where the right-hand charge is. Rank the magnitude of the electric field that is exerting a force on the right-hand charge. So what you have to do in this problem is basically you're ignoring that right-hand charge. You're looking for the field that is there. All right? So the other 2 particles, charged particles, they have fields, interacting fields, but I'm just showing you the vector nature of the field at that location. So we're ignoring the 3rd charge. We're just looking at that location right now. So it's as if that charge on the far right is not there. If we had to figure out the force, then we have to use that charge. We have to figure out the pairs of forces like we did in the notes and do the net force. Here we're just looking at a location. So it's kind of hard to, in the notes, I think I always chose locations that weren't at a spot where a charge was already located. So what I've done here is, in the diagrams, I've done all the preliminary work. The equation is E equals kq over r squared, the electric field generated by a point charge. And then I simplify it because all of these have the same k, but they have different r's. They have different r's, or different distances. But if I say let x equals 1, the basic premise here is this. If I look at far left to the right, that's a distance of 2x. Right? When you have double the distance, you're going to have 1/4 the field. And if it was a force, it'd be 1/4 the force. The same principle applies because for forces, it's kqq over r squared. It's an inverse square law. We've had a lot of, well, we've had Coulomb's, or Newton's law of universal gravity, which is an inverse square. You double the distance, 1/4 the force. Here we have, this one on the far left here is twice as far as the one in the middle from the location we're referring to. So for example here, I'm calling x a distance of 1. So I'm going to put a 1 in for r. Put a 1 in for r. So, and then for the distance from the -3 nanocoulombs, millicoulombs, to that location there, ignoring the second charge, we're just looking at location. So the math here, see if I can pull this down. Come on down. Whoops. Okay, too far. So in case A, for this middle charge, this -3 millicoulombs, and I'm going to ignore the milli. They're all millis, so I don't need to really factor that in right now. We're just looking at a comparison. So the charge is 3. The negative doesn't matter because all that matters is for direction. I mean, it matters for direction. It doesn't matter in the equation. But that's why my arrow here, that 3 in that first diagram, points to the left. Because electric fields point toward negative charges. So I'm dealing with this charge right now. It's 3 over 1 squared is 3 to the left. And then the -3 here is to the left as well. But it's twice as far away, so it's going to be 1/4 the force. So in other words, it's 3 over 2 squared. So 1/4 of 3, which is 3/4. But what is the net force there? Well, it's the sum of those two, since they're both in the same direction. It's 3 plus 3/4, so down here at the bottom here, the net field at that location is 3 3/4 newtons per coulomb. If I wanted to figure out the force right now, I could multiply that by the charge that is there. How many coulombs that is. Well, these, I don't have the right units here right now. I'm just putting in the generic units. I didn't actually put in the milli So this might be 3 3/4 or 3.75 times 10 to the negative third newtons per coulomb. I don't even know the distance because it didn't give me the distance. I said it was 1 meter. But if that were the actual units, these are proper units, but like I said, I don't have the right factor in there. But it's the right magnitude, 3 3/4. Multiply by the charge to get the force. You don't need to do that right now. But let's do another one, part B. Part B. Now, it's basically another directional thing. You start with the middle charge once again. All right, that's a plus now. So this arrow over here, the 1 to the right, the 3 to the right, that comes from the middle charge. It's the same as the start for part A, except for the charge in the middle is +3. I'm ignoring the charge that's there. This is just a field. So 3 over 1 squared is a field that's away. You're always away from a plus charge. The second one is still to the left because you still have a -3. So this -3 here is going with the 3/4 right there. So what's the net field right now? Well, now you have to subtract these two. So 3 minus 3/4 basically is 2 1/4. So that's just so we can compare B to A. A is 3 3/4. So for B, it's a smaller net field. We'll do one more and then we'll summarize. So in C, all right, now we have a 6 millicoulomb charge at a distance of x, which is 1 meter. Okay, so it's going to be 6 over 1 squared, so that's a 6. Because this is a 6, so it's a twice the charge, it'll have twice the field, and once again, it's away from a plus charge. That's the definition. They're always away from a positive towards a negative. So the positive 3/4, once again, is towards the left. It's the same as it was for A, B, and C. It's a -3 millicoulomb charge. But what's the net field? 5 1/4. So I just go through that same argument for all 6 scenarios. In scenario D, it's a 3 to the left, but the only thing that's different between A and D is that in D, this is a +3 right here. So instead of the arrow pointing towards a negative, it's away from the positive. So it's a 3 to the left for the middle charge, like in part A, and a 3/4 to the right, 1/4 of that, but to a different direction. So it gives you a net of 2 1/4. And then E comes out the same as D. It's the same thing because you're ignoring the charge that's there. It's got the same directional arrows as D for the same reasons and the same answer, 2 1/4. F, okay, there's 2 arrows here and I drew this. Now the 6, it's just like C except for you reverse the direction of your 6 Newton per Coulomb field because it's got to be towards the -6. So that big 6 right there is because it's toward, the field will be towards this -6. And it's also towards the -3. That's where the 3/4 is. So there the net field is 6 3/4. So the ranking is F, and then C. Now you can see I have the numbers all circled. F, C, A, and then the other ones are all equal. B equals D equals E. All right, I got to move this along here. This one. These are charged spheres. Charged spheres. Let me see if I can make this bigger. Yeah. Transfer of charge. 143. Okay, so you're going to touch these 2 spheres. Both of these charges, both of these spheres are missing electrons, missing a bunch of electrons, and we could just, like this one's missing 6 electrons. It's missing a bunch more than 6 electrons, but we could just make it simple. Missing 6 electrons, so if you have missing electrons, you have a +6. This one's missing 2 electrons. But when you touch these 2, okay, they're going to equalize. So once they touch, they'll both have the same charge once they've touched each other. So you'll see a lot of shortcuts here. So in A, okay, there's a total of +8 between the two. +8 between the two. So when you touch them, so what happens is, here they are separated. So these are diagrams showing what happens. When you touch them, +2 charge goes to the right, or you could say this is not another thing. It's just like a -2 going to the left. So we're taking away 2, okay, 2 more negatives. So you're making the right-hand sphere more positive. All right, you're making the left-hand sphere less positive. This is just showing you what happens. So there's more. There's a plus charge that goes to the right, or in other words, a negative charge that goes to the left. It's the same effect. All right, so 6 minus the 2 gives you 4. or the 2 plus the 2 gives you 4. So they're going to end up at 4 and 4. In case B, there was a negative 6 and positive 2, so the net between the two, the net is negative 4. It's negative 4. Okay, so when you touch them, okay, bottom line, you can think of the end result. If the total net charge is going to be negative 4, they're both going to have a negative 2. So what happens is some of the negative charge leaves this left-hand sphere, so it's going to be less negative when it's done. And then when you add 4 plus the 2 here on this ball, minus 4 gives you the negative 2 left on that right-hand sphere. And it'd be like the same thing as a plus 4 going to the left. So I kind of put 2 arrows on here showing what's happening. You can see either negative charge, basically electrons are leaving this sphere and going to that charge. That's what I'm saying. Electrons are leaving that sphere. Here, the electrons left the right-hand sphere. So I could ask you that question. Which sphere are the electrons leaving? As the electrons leave, it becomes more positive. And a negative 2 here is more positive than a negative 6. All right, so you can see a lot of shortcuts here. In the last one, or part C, a plus 6 and a minus 2, the net here is negative plus 6 minus 2 is the total charge between the two spheres is plus 4. So each sphere at the end has to be a plus 2 and a plus 2. So what happens here is literally, you know, for which sphere do the electrons leave? All right. Well, electrons leave the left-hand sphere, a plus 4 charge. So, so because this one has a lot of missing electrons. Sorry, let me restate that. The electrons leave the right-hand sphere. Okay, the electrons are leaving the right-hand sphere, coming over to the left-hand sphere, say negative 4 electrons. That's what leaves the right-hand sphere positive, right? And it neutralizes 4 of the plus charges on the left. So the electrons leave the right-hand sphere. Here the electrons left the left-hand sphere. Here the electrons left the right-hand sphere. All right? And if you keep going down here, then you can keep, oopsie. And then, then I just kind of summarized. I didn't even do the other ones. You can go back and look at the other ones. The net charge here is going to be negative 4, or negative 8. Total of negative 8, so it's going to be negative 4 on each sphere. Here the net charge is plus 6, so the final dispensation is going to be plus 3 on both spheres. And this one is going to be a negative 3 on both spheres for the final answer. So the ranking ends up being A, E, C, B, F, D. If you look at the net charge where D, okay, is going to be, because a negative 3 is less than, I think in D, A, B, C, D. Yeah, each one is going to have a negative 4, I'm sorry, negative 4 on each sphere in this one. In D it's a negative 4. On F it's a negative 3 on each sphere. That's why those are the last. And B I think had a negative 2. Yeah, negative 2. And the other ones have positive charges, A, E, and C. A is a positive 4. E was positive 3. Yeah, E was positive 3 on each sphere. So we're just ranking them by left-hand sphere. The net positive charge. Okay, the next one here. Oh, wave speed. Wave speed. All right, so these aren't very rounded. Okay, so you got to think of these as being sinusoidals. They have sawtooths, and you can generate sawtooth patterns. Don't worry about that. Just treat these as a wave. For example, in A here, the wave goes up, down, up. If I use my pen, I could round this off. So basically, it's a wave that goes up, down, up. That would be one wavelength. From that spot to that spot is one wavelength. All right. So there's two wavelengths showing there in that diagram. There's two wavelengths showing in that diagram. And this one in B, if I go down, up, down, that's one wavelength. So I'll put a line there. And then another wavelength. So if I asked you how many waves are showing here, there's 3 waves showing there in diagram B. In diagram C, there's only one wave showing, one wavelength, one cycle in that diagram. That's a little bit of a review. Now, V equals lambda F. Velocity of a wave equals wavelength times frequency. Now it tells you in this problem that the frequency is the same for all these waves. The amplitudes and wavelengths are different. I'll tell you right now, the amplitudes don't matter as far as this equation goes. Amplitudes have to do with the energy in a wave, not the wave speed. So the higher the amplitude, basically more energy in the wave. I'm going to erase some of this. Okay, so if the frequency is the same for all these waves, then the velocity is directly proportional to the wavelength. So to rank these by wave speed, which is what they want you to do in this problem, you just rank them by wavelength. All right, the biggest wavelengths are going to have the biggest speed. So the ranking would be C and D tied. C would be equal to D. They have the biggest wave speed. I can put an equal sign down here, and these A and E are both what? 3 meters, and B and F are both 2 meters. That would be proportional to the wave speed because they all have the same frequency. Pick a frequency of 1 hertz. I don't know what the frequencies are, but it says they're all the same for the particular problem given. Now, if I could tweak the problem, change the problem. Let's say, and we have to do some real deeper thinking here now, I'm going to change the problem down here. So I'm going to change the problem. Let's say the x-axis is time instead of wavelength or any other arbitrary units, which I'm not even sure what they are in this problem. Okay, but let's say the x-axis is time, and each mark is 1 second. So like if I go to diagram A, this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Those are all seconds. So that's time in seconds for all these x-axes. And then the vertical axis would be the amplitude. Now, it's a different problem. Okay, in the first situation, that axis was not time. Okay, it was, well, it could be time in part A, but they're not all the same. They wouldn't be all the same time frames. Okay, I believe if part A were they could be times, it would have to be different scales. For example, in time in diagram A here, the way I have it, it's 3 seconds for one wave. So in diagram B, this would have been the 3 seconds for one wave because they all have the same frequency. So that would have been the 3 second mark. So each mark there would have been 1.5 seconds. And in diagram C, this would have been the 3 second mark because they all have the same frequency. In the original problem, they all have the same frequency. That would have been a good question. How do the time scales compare? Well, that's how they have to compare. They all have to have the same. In order to have the same frequency, you have to have the same period, because if you go to the left here, okay, period is 1 over the frequency. And what I'm saying here in this case, in case number 1, the original problem, they all have the same period of 3 seconds. They all have the same period of 3 seconds if you put the time scale in different spots. All right? And diagram D would be like C, diagram E would be like A, same time scale, and diagram F would be like B as far as the time scale goes. If you had different time scales, that's what you'd have to do to get the same frequency. But now let's say that the time scales are all the same. So now, like in B, this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5, and 6. All right, that's going to change the problem. It's going to change our rankings for calculating V. It's going to be different velocities possibly. In the original problem, we already gave you the answer. It's all circled down there. But so here's the example now. If I use this time scale that I'm now using, same time scale on all 6, unlike the original. In diagram A, the period is 3 seconds, come down here to the right. So the frequency is 1 over 3, 0.33 hertz, because the frequency is 1 over the period. And then the velocity is wavelength times frequency. The wavelength is 3, that's given in the diagram, times 0.33, gives you 1 meter per second. Interestingly enough here, if you do the math, okay, they all come out to be 1 meter per second. So for example, in B, the period is 2 seconds. If you have 1 tick per line there, you go back up to B, all right, the time, you can look here, the period, I'll circle it in red right there, circle it in red. So the time for one wave is 2 seconds. So the frequency is 1 over 2, which would be 0.5. All right, and in C, the 1, 2, 3, 4, 5, the period would be 6 seconds. So the frequency would be 1 over 6. So I've done all the math there. I can see the frequency is 1 over 6. The period was 6 seconds to make one wave. It's the time to take to make one wave. So lo and behold, the frequency in in C is 1/6, so even if I don't divide that, it says the wavelength is 6. So if you do all 6 of these, their velocity comes out to be 1 meter per second. So if the time scales are all the same, then these all have the same velocity of these waves. So that would be a tweak to this problem. All right, one more problem here. Standing waves. Standing waves. All right. Okay. So you have to rank these by the frequencies. Once again, the equations are T equals 1 over F, V equals lambda F, but you also have, depending on the harmonic, these are standing waves, so you got to look back at your notes, and I'm going to kind of, for each different harmonic, for example, this is, well, for waves on a string, 1, 2, 3, this is the fifth, in A it's the fifth harmonic. You count the antinodes to get the harmonic. All right. So in each situation, like if I go from this spot to this spot, and if that were the diagram, if you go back and look at your notes, if that's all you had, that'd be the first harmonic. But we have 5 of those here. Each of that's a 1/2 a wave. From those 2 red dots, between the 2 dots is 1/2 a wave. If I go from here to here, that's 1 wave, because you're going up, down, back up again. That's 1 wave. That's 1 wave. So I'm recapping the notes a little bit there. Or in C, okay, I have one wave there. Basically, that's 1 wave. In part C, I have 1.5 waves. That's the third harmonic. Sometimes it's called the second overtone. All right. And in part E, I have 2 full waves. I have a wave that goes from here to here. That's 1 wave. All right. That's the second harmonic, first overtone. All right. There's 2 full waves in E. So I do this all by visual. So I can see that in E there's 2 wavelengths. So I have 2 wavelengths there. So I have 2 wavelengths in part E. I have a 1.5 wavelengths. I have 2.5 wavelengths. Okay, I have 2.5 wavelengths in that one. In part B I have 1 wave. That's 1 wave. Then 2. Then 3.5. So in part B I have 3.5 wavelengths. And in D I have 2 wavelengths, 2.0 if you want to. And in F I have 1.5 wavelengths. I have 1.5 waves, just like in C. And once again, just to highlight, that's 1 wave. If I go up, down, that's 1 wave. Okay, this is what musical stringed instruments do. They vibrate like this, plus they have a lot of these things all mixed together at one time. That accounts for what's called the timbre of the sound. All right, so now another thing, it says all these strings have the same tension and they're the same string. So we're not going to get into that calculation, but so what that means is they all have the same velocity. The velocity is constant. So that's an important thing here. The velocity is constant. And for some reason I can't change my color now. Okay, so I'm going to circle that. I've underlined it, but I'm going to circle it. The velocity is constant. All right, because all these strings, it tells you in the paragraph above that they all have the same tightness. If you tighten up a string, the velocity becomes greater, and that's how you change the frequency of a string, by changing how tight it is, and changing the velocity. But all of these strings have the same tightness, and they're the same strings. You know, fatter strings have a different velocity as well. Like on a guitar, there's a thin string, and I don't know what the notes are for each particular string. Same thing in a piano. The strings that get bigger and fatter, or longer and shorter, to change the velocity and change the frequency that's given off. But here we have the different harmonics. But in the equation down here on the left, V equals lambda F. Okay, if I solve that for F, down here on the left, F is V over lambda. But the velocity in all these waves is the same, because they have the same tightness, same type of string. So the frequency is related to 1 over the wavelength. In other words, as the wavelength goes up, the frequency goes down. In A, I've already written it down. There was 2.5 wavelengths there. If you go back and look, 2.5, I have it written down right here, 2.5 wavelengths. And the length of the string is 25. So in 25 centimeters, I have 2.5 wavelengths in 25 centimeters. All right? So the length of that string, 25 centimeters, contains 2.5 wavelengths, so the wavelength is 10 centimeters. You do the same thing for B, C, D, E, and F. In B, I said there's 3.5 wavelengths. You can go back and look at that. And it tells you in the problem above, it's a length of 28 centimeters. It's a different length string. So 28 divided by 3.5 gives you 8 centimeters. So this gives you the wavelength of each string. Okay? And you just take the length that's given, divide by how many waves you see, and then you calculate the wavelengths in each of these scenarios, 6 scenarios, and then the ranking is by inverse wavelength. They want you to rank these by the greatest frequency. Well, the greatest frequency will be by the shortest wavelength, because frequency and wavelength are inversely proportional. So the greatest frequency will be B, and then A and E tied, and then D, C, and F. I think I wrote that down here. Yeah. B is the greatest because it's the smallest wavelength, biggest frequency. A and E tied. D, C, and F will have the lowest frequency. Biggest wavelength will give you the smallest frequency. All right, that's the critical thinking for this unit.